Hi and welcome to Geeks for Geeks. Can I have a quick +1 in the chat if I'm visible as well as equally audible? Let me just turn on my preview screen so that I know that yes, I'm visible or not. Okay, if you face any difficulty regarding my audio, just let me know. Hey Sushil Kumar, Satyabrat Ojha. Hi Satyabrat Ojha. Hi Sushil Kumar. Okay, so we have 8 people, but only 2 of them has responded. I can see, I can hear you. Thanks a lot, Prince. Okay, so if you have any problem regarding my audio quality, just let me know. Okay. So, but before that, I feel that there is a cracking sound from behind. Okay. Yeah. Now it's fair. Okay. Now the audio quality should be absolutely great. Okay. Today we would be learning a very important concept. Okay. First, we would be diving deep into what? We would be diving deep into a data structure known as DSU, which we first need to implement it and then we need to use it. And then we would learn a algorithm. Okay, yeah, thanks a lot, Shailendra. I thought that it is not clear. Okay, Satyabrat, thanks a lot. Okay, so today we would be learning about a data structure. Not able to hear now. Okay, thanks a lot, Prince Kumar. Okay, so today we would be learning about a data structure known as disjoint set union. Okay, disjoint set union. Okay, and this data structure is absolutely very simple, but you need to understand two rules of it, and you need to do a little bit of dry run of this approach. Okay, see, you need to have build up a solution in a dry run, write it in a pen and paper, and you need to see it yourself how it is working. Okay, fair enough. Now first we would be learning why do we need DSU. Okay, first we would be learning why, then we would be learning how, and then we would be learning about when do we use DSU, and we would be talking about two things. First, we would be finding a loop in a graph. Okay, so first we would be talking in terms of loop detection, which can also be done without using DSU, but I would be showing you with the use of DSU. And then I would be telling you a approach of a query based problem, but as you are not well versed with the offline and the online queries, I would just skip it a bit, but I would give you an overview of that. And then we would learn about minimum spanning tree. Okay, minimum spanning tree. Okay, which which can be solved using two things, that is Kruskal's algorithms and Prim's algorithm, but we would be focusing on Kruskal's algorithm because that is enough. Okay, Kruskal's algorithm, this is what we would be doing today. First, so this is the overview of what you would be getting. So if you're not here for these all things, then don't waste your time. Okay, because your time is absolutely very precious. Okay, fair enough. Now without further ado, let us start. So suppose first we want to know why do we need one more data structure to be used. Okay, now suppose you want to add edge add edge okay, add edge, and then you want to count the number of components, count the number of component, and then you want to count the, suppose cycle is present or not. Cycle is present or not, and you want to know that if two two nodes are present in the same component or not. Two nodes in same component or not. Same component or, by the way, trust me, just a bit of off topic, but that's absolutely great. So by the way, when we started, we have a 3.5k views in the first video itself, but I knew that gradually it would fall because I have experience over this. But this thing which is remaining, that is the 11 students which are remaining, they are so enthusiastic that they don't worry about other things. They just say that yes, Siddharth should start, and that's absolutely commendable, trust me. Okay, now suppose you want to do this only once. If you want to do this only once, then adding an edge, counting the number of components, cycle is present or not, two nodes in the same component or not, okay, we can do it using a simple DFS. Like, I would give you an example. Now, what do you mean by component? I told that by component. So let us just discuss quickly about component, because this is not what I have discussed. So yeah, 13 students. Okay. So, but I have appreciation of 195 students, so that's much great than that. Okay, so now let's talk about a little bit about components. Now suppose we have 1, we have 2, and we have 3, and then we have 4, we have 5, and then suppose we have 6 here. Okay, now suppose this is there, then this is there, and this is there. Now what do you mean by component? Component means that I can travel from any node to any node. Now suppose I want to travel from 1 to 2, I can do that. I want to travel from 2 to 3, I can do that. So from any node to any node I can do that. Apart from that, nothing is component. So basically क्या होता है, एक group of nodes जो interrelated है, that is known as component. So this would be component 1, and same way this would be component 2, this would be component 3. Now, how do I tell that this can be solved using simple DFS? I tell this because if I start a DFS from this node, I would be visiting this node and I would be visiting this node. Then after this, the DFS would stop. Then I need to come to this, visit this, and then I would visit this. Then दो बार DFS चला, and then again I would visit this. DFS कितना बार चला? 3 times. 3 times the DFS is done. So the number of times the DFS is done is equal to the number of components. Fair enough? And what you can do is, as you would visit at each DFS traversal, you can keep saving it in the vector itself, and you can say that yes, these all component contains these all nodes. Okay, fair enough, you can do that. And after you do that, you would be able to tell if two nodes are the same component or not. So you just need to tell which is the, suppose this belongs to this belongs to this. If they don't belong to the same thing, you can keep it in a set or in a map or in a priority or in a multiset, and you can just check if they belong to the same multiset or not. And if they don't belong to the same multiset, that means that they are not in the same component. And the second thing is the cycle is present or not. Okay, cycle can be easily told by the parent and a child relationship. If we are again visiting it, then that means we are doing that. Okay, now suppose ये तो हो गया. This is one part of the question. Now suppose I want to check all of these at each iteration. If I want to do this at each iteration, I don't want any DFS or something. because DFS would obviously have the number of nodes, so we would be visiting all the number of nodes, and visiting each node would have big O of 1, and visiting n nodes would have big O of n. So basically we would have a big O of n into 2 to the power 4. So basically we would have a very big time complexity. Time complexity would be very huge. But I want a lower time complexity, and I want to do it at each iteration. And you can relate it with the use of priority queue instead of sorting. Sorting means last में जितना वैल्यू आया उसको सॉर्ट करके बता दो. बट प्रायोरिटी क्यू क्या करता है, हर एक स्टेप में जैसे आप एलिमेंट्स इंसर्ट करते हो वो अपने आप उसको प्रायोरिटी वाइज सॉर्ट करते रहता है. ओके, फेयर इनफ. नाउ आई टोल्ड द डिफरेंस. नाउ टेल मी इफ ऑल दिस थिंग्स आर क्लियर टू यू और नॉट. ओके, I would tell you again. I want to add an edge between two vertices. I want to count the number of components. I would do that by using a simple DFS. And cycle is present or not, I can do that also. And two nodes are present in the same component or not, I can do that simply by using a multiset. Okay, but I want that at each iteration. I want this to be done at each iteration. Now, do you understand the need of the hour or not? Just tell me quickly. Tell me if you understand this or not. Why? What is the thing that I want? What is the need that we are talking about? Just let me know quickly. Let's have an upper bound to this waiting. So we would have a countdown of, let's say, 1 minute. And quickly tell me if things are clear to you or not till this point. Okay, Satya Bharat Ojha, it's clear. So at any point, suppose 1 is not clear, 2 is not clear, just let me know. I would do that. And that is my duty. Just quickly tell me that. At any point if you're not able to understand. Ankit, thanks a lot. Sumidhe, thanks a lot. So we still have 10 to 2. What is need to do it? What is the need to do it at each iteration? Suppose that is the question. See, if I frame a storyline out of this, it would be very difficult to understand. That's why there's the problem. What is the problem? What is the need? Suppose there is a problem like this. Suppose a problem hai वैसा. Suppose I would tell you that this is there is a problem on CSES problem set. That suppose a city is there and I want to build roads, construction, and the name of the problem is construction. And in that problem, we are told to do something like this, that if they belong from the same place, then we don't need to build a city, build a road, and we build a road. Build a road means what? We build an edge. Okay, and a road can be built or not. That means that we need to check if there a cycle is present or not. Okay. Dhruvesh Paul, again one more. Which one more? Tell me the point at which you want the one more. Okay, fair enough. Let's proceed after this point. So I would tell you, suppose there is a group of students. Okay, suppose there is a group of students like you. Okay, and there is one more group of students like you. Okay, now suppose I find Satyabrat Ojha each day. So what I decided is make him the representative of the class or the class representative, that is Sia. And this side I find, let's take a name. Yeah, this side I find Lalit extremely active in the class. So I make him the CR. Okay, so this one is Satya and this one is Lalit. Okay, fair enough. Suppose this is the thing. Okay, just a simple class of students and one is elected as CR and in the other class also one is elected as CR. Now suppose this student is having a problem with something. What he would do is he would report to this CR. Now suppose this student is having a problem with something and then he would report to this CR, that is Satyabrat, And then suppose this student is having a problem with something. So will he go to that CR? No. Why will he go to that CR? He would just come to this Lalit and he would say that yes, this is the problem, can you just solve it? And this one, and he would need to solve it. This is what he needs to do. Fair enough. Just a simple scenario of what we have experienced back in our old days. Fair enough. The same thing would be done here also. Here also we would elect a representative of a particular component. Okay. Here this can be thought of as a big component. This is component 1 and this can be thought of as a component 2. And for each component we would have a CR of them. Okay. Now suppose I don't go in politics, but still I have that much of knowledge. Now suppose these two CRs have a meeting, joint meeting, and they just try to have a Gathbandhan kind of thing, and what they tell is, let's come together and let's build a better community out of this. Okay. Now what would be done is, now Satyabharat and Lalit would work together. Okay, work together. They would both work together. Now what would happen is, they both would belong to the same thing. Okay, and basically what we are doing is, we are adding a edge. Now remember this scenario, and this scenario would help a lot. Okay, help a lot in whatever we are going to learn. Okay, and you would see that, yeah, Lalit, manage structure in corporate. Yeah, you are more into corporate, so you would be getting a hang of it. So let's start doing it. Now suppose what I want to do is, I want to have a structure like this. Okay, and I have a structure like this. Okay, now we need to have two arrays. Okay, by the way, to be honest, I was never the CR of my class, and if you just talk about me, I was the worst of the class. I was always a backbencher, always doing nuisance in the class. Okay, so trust me, I'm also not like the nerd, same old nerd. Okay, I'm a backbencher where people scold me a lot. I get scolded a lot. Okay, for everything I do. So let's just go whatever we were talking about. So this is 2. So let's just, yeah. So this is 2, this is 3, this is 4, this is 5. This is 2, this is 3, this is 4, this is 5. Initially what we would see is, everyone, suppose a new child came to the class. Okay, a new child came to the class and he is unaware of these all CR system. ये सब मोह माया से दूर है. Okay, now suppose this person doesn't know of CR thing, so he would be a CR of his own. He needs to take care of his own. So initially everyone is a parent of itself. So 2 is a parent of itself, 3 is a parent of itself, 4 is a parent of itself, 5 is a parent of itself. So if everyone is a parent of itself, then the size of each component would be 1. So the size of each component would be 1, 1, 1, 1. Okay. Now let's just move forward. Okay, now I want to add a edge from 2 to 3. Okay, and this is popularly known as the parent array. Parent array, and this is known as, okay, rank array. And why this is known as rank array, we would talk about it. Okay, but initially, for just for understanding, this rank array is not that much important. When we would optimize this and we would see why do we need optimization, then this rank array would be very much needed. Okay, but for now you can just ignore this rank array. Okay, now suppose I want to connect 2 and 3. So to connect 2 and 3, we would make 3's parent as 2. 3's parent would now become 2. Okay. Now we want to connect 3 and 4. So what we would do is, we would make 3's parent as 4 and we would mark it. So 3's parent would be, 4's parent would be 3. Yeah, 4's parent would be 3. We would just make 4's parent would be 3. Now, while we are merging the nodes, suppose there are two nodes and we are not able to figure out who would be a parent of what. This one would be a parent of that, this one would be a parent of that. Okay. Initially, just take that we are doing a random calculation, but as we move forward, we would see how we are doing that. Okay. Fair enough. So let me just remove. Yeah. So now this is the rank array, this is it. So initially we have 2 to 3. So we come from 2 to 3. So we would say that 3's parent is 2. Okay. Then we come to 4. So we come to 4 from 3. So 4's parent would be 3. So 4's parent would be 3. Okay. Now we come from 2 to 4. So 4's parent would be 2, but that is already updated. So we would just say yes, 2 can also be there. Now we come from 4 to 5. So 5's parent would be 4. Okay, 5's parent would be 4. Now we again come from 2 to 5. So 5's parent would be again. So 2's, yeah. So yeah, this is updated. Yeah. So now we can see that 3's parent is 2 and 2's parent itself. So if I want to find the parent of 3, what I would do is I would go to 3 and I would ask who is your parent, and he would say that 2 is my parent. I would go to 2 and we would keep moving forward till we find a person who is a parent of himself. Okay, finding it a little bit hard to understand. Okay, fair enough. I would make it a little bit easy for you. Okay, let's take a good example where we don't have any cycles or something. Okay, so let me just remove it and you would get a better hang of it, because when we take cycles it is a little bit difficult to understand. Okay, now suppose we have a tree like structure, 1 and we have 2 and we have 3. From 3 we have 4 and for 4 we have 5 itself. Now 1 2 3 4 5, 1 2 3 4 and 5, 1 2 3 4 and 5. Everyone is a parent of itself. So 1 ka 1 parent, 2's parent is 2, 3's parent is 3, 4's parent is 4 and 5's parent is 5. And if it is a parent of itself, if someone is looking after himself only, then the size of it would be 1. So the size of 1 is 1, the size of 2 is also 1, the size of 3 is also 1, the size of 4 is also 1, the size of 5 is also 1. Now from 1 I would go to 2. Okay, so 2's parent is 1, so 2's parent is 1. Now I would go to 3 also, so 3's parent is also 1. So I would say 3's parent is also 1. Now from 3 I would go to 4, so 4's parent is equal to 3. I would go to 5, 5's parent is 4, so 5's parent is 4. Now if I want to find the parent of 5, what I would do is I would say 5, who is your parent? He would say 4. 4, who is your parent? He would say 3. We are climbing upward. Okay, Now 3, who is your parent? 1. Now we would go to 1. 1, who is your parent? It is 1 itself. Okay. So we would say that yes, it is a parent of itself. So we can find the parent. How? Ask the parent. Ask the parent. Keep going till we find a node which is the parent of itself. Keep going till we have a node which is a parent of itself. Fair enough? Keep going till we have a node which is a parent of itself. Now we would do that and we would write the code of it also. Okay, and this would get updated accordingly. Now how would this get updated? Let's take one more array, and here we would have multiple components. Okay, so this would be 4, and here we have again 5, and we have 6, and then suppose we have 7. Okay, now we also have a array of parent, and this time we would update the rank also. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 2, 3, 4, 5, 6, and 7. We would copy the same thing and we would keep it down, and this would be the rank, and this would be the parent. Okay, and the rank would be 1, 1, 1, 1, 1, and the parent would be itself. Fair enough? Now let's start doing that, and this time we would update the rank also. Now we have from 1 we would move to 2. So 2's parent would be 1. 2's parent would be 1. So 2's parent is 1. Now we would come to 1 to 3. 3's parent is 1. So we would update 3's parent as 1. Now we would go from 3 to 4. 4's parent 4. So we would go from 3's to 4. So first we would find 3's parent. 3's parent is 1. So 3's parent is 1. 4's parent is 4 itself. Okay. Now what we would do is we would say that 4, your parent is 1. So 4, your parent is 1. Okay. A slight change is there from the last time. This time what we are doing is we are finding the parent and we are merging the parent, if you could observe. Okay, and this is the idea. Okay, then this is complete. Then we come across 5. 5, parent is 5 itself. So parent of 5 is 5 and 6 is 6. Okay, so 5 so 6, your parent is 5. Okay, now let's update the rank array also. Okay, accordingly. So rank array we would update at the same time, but here we are updating it individually so that you would also know how we are doing that. Okay, so I want to just merge 1 and 2. So who is the parent of 1? 1's parent is 1 and 2's parent is 2. So I would say that whatever is there in 2 would also come under 1. So 1, so 2 mein kitne hai? 1. So it would be updated by 1 plus 1, that is 2. Okay. Now I want to merge 1 and 3. 1 parent is 1, 3's parent is 3. So I would say 1 plus the rank of 3. Whatever is this side would get merged to this side. That would get added whatever is here. So this would be added to 3 and this would remain as it is. Okay. Now 4 parent is 4 only, and 3's parent is 1. So 3's parent is 1. 1 is having a value 3. 3 plus the value of 4. That would be 3 plus 1, that is 4. So now 1 has a value 4. Okay, 1 has a value 4. Now let's go to 5. 5's parent is 5 only. Yes, and 6 parent is 5. So 6 number of nodes in 6 would get added to 5, and that would be 1 plus 1, that is 2 itself. Then we come across 7, there is no edge, so we won't do anything. Now let me show you a magic. What is that magic? Now if I want to know the number of nodes in, let's take any node, let's take 3. So 3's parent is 1. So I can go to 1 and I can ask what is the number, and it is telling me the number of nodes in 4 is in the component where 3 is there is 4. And I can go to 2. First I would find the parent of 2. Parent of 2 is 1. 1 is having how many elements? 1 is having 4 elements. So I would say that 2 जहाँ पे है, जिस component पे है, उसमें 4 elements है, 4 nodes है. My laptop just got freezed. Okay, we have it. This would hopefully go away because I have something big coming up. Okay, now let's take the value of 7, which there was no edge. Now let's go to 7. 7 is a parent of itself. So let's go to 7 and ask him. Okay, this is 1. That's great. Then we come to 5. 5's parent is 5 only. So I would come to 5 and ask him, and it has telling me 2. So the component in which 5 is there is having the value 2. Now tell me if all this dry run went to your head or not. And now we are able to tell the size of each component. And initially we can take the number of component as n itself, and we can keep decreasing it as we do it a merging operation. Okay. Hi Peaky Blinder. Okay, thanks a lot Lilith. Thanks a lot Peaky. So quickly tell me, others quickly tell me if things are clear to you or not. So let's wait one more time. Let's wait one more minute. So I think that people are trying to digest it. So I would give them one more minute to digest it, and then we would start writing the code itself. Then we would talk about 2 more optimization, and I think that I need to end the class today itself. By the way, we would be having some sessions on Zoom and that rank array again. Okay, so basically what we are doing is, rank array में क्या कर रहे हैं? Rank array में first we are finding the parent. Both, suppose there are 2 nodes. इसका parent खोज के निकालना है, इसका parent खोज के निकालना है. उसके बाद suppose this is having 5 elements, this is having 10 elements. तो बेसिकली क्या कर रहे हैं कि जिस पे मर्ज कर रहे हैं, सपोज इसको इस पे मर्ज कर रहे हैं, the number of elements here would get merged here, and now both would have this thing. So now suppose this has 2 elements and this has 3 elements, and I'm trying to merge this 2 elements into 3. So this 2 would get added to 3, and this would have 5 elements, and this is now, and this is it. Okay, and you would get a hang of it when I would code it also. Okay, so let's start the coding thing. Okay, let's have, so let's just directly, so what is there is that, suppose I suppose I want to use disjoint set union. Okay, suppose I'm giving a contest and I want to use disjoint set union. So in the first place itself, I won't start implementing disjoint set union and then I would start doing it. That's absolutely time taking. In the first place, while you are trying to practice and while you are trying to get a hang of it, that's absolutely fine. But as you move forward, you need to have a proper library of your own. And as we have less time, we have approx 17 minutes to 17 minutes 20 minutes. So I would be directly giving you the best implementation out of it. So we would use a struct to implement it. Okay, and we would name it as union find. Okay, we would name it as union find. And then the first thing that we require is the number of nodes, and the next thing which we require is the number of components that we would be maintaining. So I would just write component, cp component, and then I would need a parent array, and then I would need what? I would need a rank array out of it. Okay, and then I would need the default one, and then we would make it a parameterized construct. Okay, so union find over int a, and then we would have something like this, and then initially the number of nodes are all individual, so everyone is a parent of itself. So initially we have n component, that is what I told. So n is equals to number of components, the first thing. And now we would make a parent array, okay, which will be new int. Okay, so parent is equals to new int of size n plus 1. Okay, new int of size n plus 1. Why? Because it might be the case that it is one indexed. And then we have the rank array, which will be equal to new int of n plus 1. Okay, this is it. Okay, and then we would like to have the find method. Okay, but before that, what we need to do is we need to make everyone a parent of itself, and then we want to make the size of each component as 1. So let's have a for loop int I is equals to 0, I is less than equal to n, and I plus plus. So initially everyone is a parent of itself, parent of I will be I equal to, and let's name it as par. Okay, because naming it as parent every time would be a lot difficult. So everyone is a parent of itself, and the rank of each I is equal to I itself. So this is the first one, the parameterized constructor. So let me know if you are able to understand this or not. So initially we are having the number of components is equal to the everyone are small things. So everyone is a parent of itself. We have that, and here we are making two arrays, and then we are making everyone a parent of itself, and initially the size of each component is equals to 1. This is what we are doing. Okay, then we have the first one, that is the find function, where we find the parent of a particular, so we give it a node and it would return us the parent of a particular node. And how we would do that? Int find, we would take a number int x. If parent of x is equal to x, that it is a parent of itself, then we would return that yes, this is your parent. Okay, everyone is a parent of itself. Else Else what we would do is we would keep finding the parent. Return find of parent of x. We would keep diving deep, parent of that. Now we have the parent. Now the next thing what we need to have is the merge operation. Okay, now the merge operation is a bit tough. Why? Because suppose we have 1, we have 2, and we have 3, and we want to merge 1 and 3. So if we want to merge 1 and 3, there is no point in it. Why? Because the number of component won't get affected. The number of elements in each component won't get affected. So we won't do that. And we would talk about one more use case of this. Okay. And which is quite clear from the example, from the drawing itself, but still I would discuss it. So we would have it as Boolean merge, and we would take two values, int x and int y, and we would make it as x is equals to find of x. First we would tell that yes, first go and bring your parents, and then I would say the same thing to y also. First go and bring your parents. Okay, so if x is equals to y, that is they belong from the same component, return true, return false, or you can say quickly that return 0. Else what we would do is rank of x plus equals to rank of y. The number of elements in y is getting added to x. Okay, and then we would say that parent of y is equals to x. We can do that, and we would have a proper way out of this. Okay, so this is it. Okay, this is it. We would have the parent array, we would have the parent, and you can also have a reset and also have a print or something, but I'm not doing it because that is a kind of out of the scope of this syllabus. Okay, and you can do it on your own, to be honest. Okay, now tell me if you have any problem regarding this initialization, find function and merge function, specifically the find and the merge, because initialization I don't think you would be having a problem. And then we would discuss a way to optimize this, and we would discuss a problem that this one is having. So quickly tell me if you have understood this or not, else I would be more than happy to explain you again. Just quickly tell me if things are clear to you or not. Let's have an upper bound to this waiting. So let's just say that we would just wait for 1 more minute, and quickly let me know your feedback if you have understood this or not. Quickly let me know. Yogita, thanks a lot. Satyabharat, Yogita, Ankit, Lalit, and then we have Durvesh, Prince, and Mukamala, and Sushil. What about you all people? Did you were able to get this or not? Satyabharat, now you are able to understand the rank thing or not? How we are updating the rank? Okay, fair enough. I don't find any people responding, so let's have one more waiting towards this. So you can take your time, digest the code, and then we can move forward. That's absolutely fine. But let me know so that I can move forward. Samit Tripathi, elaborate. The session is the session is 3/4 over. So just the last 25% is remaining. So I think you can save your as well as my time by just watching the recording again. And if you have any doubt, just ask in the Telegram group itself. Okay, that's absolutely fine. That's absolutely fine. Okay, fair enough. So we have the find and the merge one. Now, let's just see a scenario where this find function would be a little bit difficult. Why? Let's just say that we have a tree like this. So we have 1, then we have 2, then we have 3, then we have 4, then we have 5. So in this scenario, suppose I want to find the parent of 5, then I would say that who is your parent? 5 would say 4 is my parent, and 4 would say 3 is my parent, and 3 would say 2 is my parent, and 2 would say 1 is my parent. So basically we need to do an operation, an operation, an operation for each find. So if we do n find, then we would be doing n square operation. So if we are doing n square operation, then why didn't we do DFS? Okay. So what we can do is we need to simplify it a little bit more. And this kind of tree is known as skew tree. Okay, just for your information. So what we can do is, suppose I say that 5 your parent is 4, 4 your parent is 3, 3 your parent is 2, 2 your parent is 1. So as we come down in the recursion, we would say that 2 your parent is 1, remember that. 3 your parent is 2, just remember that. And 4 your parent is 1, just remember that. And 5 your parent is also 1, remember that. So in how this would help, once we would do an operation, but next time as they are remembering their parent, they know their ancestors, so they won't go up in the tree. Rather, if we just come and ask this 3, they would surely say that yes, 1 is my parent, yes, 4 is my parent, yes, 5 is my parent. Okay, so we just need to save the answer while in the process of returning. So what we can do is we can say that parent of this particular x is equal to this. Okay, and we can simply return after that. We are saving the values. This small little optimization might look very small, okay, but its use is significant. Okay, so we now have saved it from the skew tree. Okay, now I would tell you, and this is known as, this whole thing is known as path comparison. Path comparison. Okay, this whole thing is known as path comparison. Now let's discuss one more scenario. Suppose we have 1, we have 2, we have 3, we have 4, and we have 5. And here we have 6, 7, and we have 8. So this one is having 3 elements. It's quite clear from the picture itself. And this component has 5 elements. Okay, this component has 5 elements, this component has 3 elements. Now suppose they have decided that 1 and 6 should now make a Gadbandhan out of them. Okay, 1 and 6 should now have a Gadbandhan between them. Okay, so in this scenario, who should be the parent? Okay, what I claim is 1 should be the parent. But why? Why should 1 be the parent? Okay, 1 should be the parent because if the smaller tree merges with the larger tree, then the length would remain same and the length would remain log n. So I can simply say the reason as to maintain log n length. I can say that. Okay. That is why, suppose this is a small tree and this is a large tree. So if the small tree is the CR, then this large tree would need to report this. So the length of the tree is getting increased. But if the large tree is the CR, then this small tree would report to that. The tree is getting large, but the length is the same. So the length is maintained. So now we need to travel only log n operation. Okay. So initially we were having a skew tree. So if we are having a skew tree, we are saving the result. Now we are maintaining the length also. So now log n pe bhi we are saving the answer. So we are optimizing it further of log n. So how can this be done? We need to check whose size is greater. If the rank of x is greater, so I would simply say if rank of x is greater than rank of y, so what I would do is rank of x plus rank of y, whatever we have done. Okay, else just the opposite of it. Okay, rank of y is greater, so we would say that rank of y is plus the rank of x. Okay, and then parent of x is equal to y itself. Okay, this would be done. So now the smaller tree would merge with the larger tree. Okay, so now this optimization would make it less than log n, and the time complexity would be Ackermann function of log n. And you can just and this is a small constant if you want to have a bird view of it, but if you want to understand it in depth, consider reading about it. Okay, so now let's do a simple question over this. Okay, let's see a use of this. Now detect a loop in a linked list, and this would be the last question and the concluding question of this. Detect loop in a graph. Sorry, I always tell detect a loop in a linked list. I'm so much obsessed with that question. Fair enough. So let's just quickly see. Suppose we have 1, we have 2, and we have 3. So we have something like this. Okay. So let's have a rank and let's have a rank array and the parent array. Rank and the parent. This would be the rank and this would be the parent. So 1 is the parent of itself, 2 is the parent of itself, 3 is the parent of itself, and the rank of everything would be 1 itself. So we say that 1 would get attached with 3. So 1's parent is also 1, 3's parent is also 1, and the number of node in 1. So initially 1 is having only one element, 3 is having only one element. So initially both is size is also equal and the parent is also same. So we would simply make any one of them as parent. So I would say the rank of 1 would get incremented by 1, and 3's parent is now 1 itself. Okay. Now the next 1 and 3 is now attached. Now we have 1 and 2. 2's parent is what? 2's parent is 2 only, and so this is 2 and this is 1. So 1's parent is 1 only, but the size is 2. So this 2 would get so yeah. So rank is equals to 2. So this 2 would get added, that is 1, and 2's parent would now become 1. So I would also have an edge over this. Now, as soon as we have a cycle, now now we have to build a edge between 3 and 2. 3's parent is what? 3's parent is 1 and 2's parent is also 1. So whenever we try to merge an edge and the parent are same, at this point we can say that yes, a cycle exists. Okay. So before merging, this would be just before merging. Okay, before merging this thing. So before merging, find parent of both, that is P1 and P2. So if P1 and P2 is there, if P1 is equal to P2, that means a cycle exists. A cycle exists. If P1 is not equal to P2, that means cycle does not exist. Cycle does not exist till this point. A cycle does not exist till this point. Hi Jai Paswan, good evening. Okay, fair enough. So this is how we can do that. Okay, fair enough. So today we learned about, okay, so just tell me if things are clear to you or not, and I would be ending this stream. I know today was a very bit theoretical, but I tried to make it as simple as possible. Now we learned about disjoint set union. So we learned about adding an edge, counting the number of components. This was the need, and the cycle is present or not, and two nodes are in the same component or not. Okay, no, I have not said Siddharth Malhotra. I am your brother. Okay. Okay, so we added an edge and count the number of components. So basically we went to each component, found the rank, and it would tell us the number of elements in that particular component itself. Now a cycle is present or not. So basically before that merging part, we try to find the parent. If the parent is equal, that means a cycle exists and two nodes are in the same component or not. So what we need to do is we need to find the parent of both. If the parent of both belongs to the same component, that means they belong from the same component. No, I am not Siddharth Malhotra. I am your brother, Siddharth Hazra. Okay, so basically doing DSU is like having a CR of a class. What we do is we have a CR and they have a Gadbandhan kind of thing, and they add a edge between them. The same thing would happen at this position also. We also have a parent array, we also have a rank array, and we do that. Now while in the process of doing, we found that there was two problems. The problem existed when there was a skew tree. In this skew tree, we had to travel top, then top, then top, then top, then top. So we need to travel all the n nodes that were there. So if it is a skew tree, we need to find all the n. So for n findings, we need to do n square operation. So what we can do is we can just remember it, and this is known as path comparison. As we move forward, we learned that we need to merge the small tree into big tree to maintain the distance, to maintain the log n distance, and that would improve the time complexity to a very great level. Okay, and the Ackermann function multiplied to the log n, and Ackermann is basically a constant, and you can read about it, have a deep understanding over it, but that is not required. But when we want to find a cycle in a linked list, we just ask the parent and keep going till we have a node which is the parent of itself. This is the algorithm, the find function. Then we move forward and we learned about component. Okay, and then we found detect a loop in a linked list. So whenever before merging, we just check the parent of both. If the parent of one is equals to the parent of two, then we found that a cycle exists, else a cycle does not exist. Okay, fair enough. So accommodating all these things in the same class itself was a very big challenge to me, but still I tried my level best, and all the questions will be provided to you in the course page itself. By the way, we would be having Zoom sessions too. So make sure you enroll in that, okay, to get the access to the Zoom session. So that's it for today. Thank you and have a nice day. Good night, everyone. Okay, so let's just wait last 1 minute to see if there is any doubt or not. And after the completion of the 1 minute, we would just end this session. Thanks a lot, Yogita. And if you have any problems and you want to discuss it individually, you can connect with me on LinkedIn. Okay. Else, you can just text me on Telegram itself. You're most welcome, Sumidhe. Thanks a lot, Lalit. Good night. And the questions of these all things would be provided to you. Good night, everyone. Sleep well. Keep coding.